My guest today is Dr. Steven Bos, an associate professor at the University of South-Eastern Norway. For almost a century, computers have relied on binary. Dr. Bos asks a simple yet radical question. Why stop at 2? By embracing ternary logic using a base 3 number system instead of binary, we could design smaller, faster, and more secure computers. In 2019, Dr. Bos co-founded the Ternary Research Group at USN with Professor Henning Gundersen. This is one of few groups in the world dedicated exclusively to ternary computing, and its mission is to develop efficient, low-power electronics by exploiting the advantages of base-free systems. Dr. Bos earned his PhD in technology at USN, where he currently teaches numerous courses in computer science and electrical engineering. His thesis, Beyond 0 and 1, explores why binary became dominant, examines the benefits and challenges of multi-valued logic systems, and demonstrates practical implementations of ternary computing. It's a fascinating piece of work that provides a clear, structured foundation for anyone interested in base-free computing. I have provided a link to it in the description. If you find our conversation insightful, please leave a like, subscribe to the channel, and if you can, share this video with a friend who might also find it interesting. This is the best way to help me have more fascinating conversations like this one in the future. Without further ado, here is Dr. Steven Bos. For the listeners who are new to the subject, what exactly is ternary computing? Could you go a bit into detail on that?
Yeah. So perhaps it's easier if I share my screen.
Yeah,
and
please.
Then we could go over parts of a presentation I gave in Berlin. A presentation called Less is More in 2024. It covers quite a bit of the questions that you might have, but interrupt me at any time, right? If you need any clarifications or anything, just let me know. So, ternary. What we see here is a SPICE simulation. A SPICE simulation of a circuit. In this case, it's a flip-flop, a ternary flip-flop. And the first thing that you should notice is this green signal on top, which is a clock signal, a binary clock signal, right? It goes from low to high, from 0 volts to about 0.9 volts. And this is clearly a binary signal, right? It goes only up and down. And then you see in yellow a ternary signal that also has a middle value of 0.45 volts. And this is the input signal to this data flip-flop. So the input at the start is 0.45, which could be a logical 0 if we talk about balanced ternary. So balanced ternary goes from -1 to 0 to 1. And then we can say a -1 is 0 volts, a 0 is 0.45 volts, and the 1 is 0.9 volts. We could also use dual power rails, and then you could have, let's say, -0.9 volts for a -1, ground or 0, and then VDD or 0.9 volts for logical 1. Right. So there's multiple interpretations of the signal. We could also interpret it as unbalanced ternary. So unbalanced ternary is using 0, 1, and 2. And then you would have the interpretation of 0 volts being 0, 0.45 volts being a 1, and 0.9 volts being a 2. We also have this sort of fractional interpretation, 0, half, 1. Well, I don't consider this really useful. So the signed version, the balanced version, is obviously, or not obviously, but I will explain later why this is the most interesting one. And then we have the unbalanced version, which is the unsigned version of the ternary. I also should mention binary coded ternary. Binary coded ternary is this interpretation of 2 bits for 1 trit, which is obviously not efficient because you lose 1 state, right? So 1 state is redundant. However, several papers also demonstrated by encoding more information in your bits, you reduce the amount of bit flips, for example, and you have more efficient data paths.
But to summarize, there is still some benefit to using binary coded ternary. We don't necessarily need to have ternary hardware. We can just use binary hardware, and there is still some benefit to that encoding.
Yeah, so that's interesting, right? I was surprised by that as well. Obviously it's not a space thing because you always lose space. So there's a lost state. You use 3 out of the 4 states that are available. But the information that is encoded will result in less bit flips, and that's what and that's the result of the encoding. There's a couple of papers that you should definitely read or mention to your viewers, especially this. I think it's called Reichenbach. He has a redundant risk. I'm not sure which what the paper is called, but that paper is going through the whole works to also simulate it using PDKs, so like to really simulate it on a chip with not the latest and greatest technology nodes, like 130 nanometers, I think, but it's still quite good. And then there's other people like Microsoft Research. We will talk about that a little bit later. That also use an encoding like this for their neural networks, and also demonstrating a real benefit there. So surprisingly, right, that you could do with this encoding scheme go beyond the let's say uncompressed interpretation of information.
I would have to imagine that this also has to do with the natural benefits of balanced ternary, like the improved representation of negative numbers, the rounding. Could you maybe go a bit more into that? What are the benefits of balanced ternary?
One of the benefits are negative numbers. So negative numbers are encoded into the interpretation. So for binary, you need to choose complement. All right. With unbalanced ternary, you could use 3's complement. But for balanced ternary, you just have the negative numbers encoded into the interpretation. That's again a benefit for bit flips. Why? Because if you go from a positive number to a negative number, then binary with the 2's complement rule needs to flip a lot of bits. And every bit flip is a cost power, right? It's dynamic power consumption. And this is not so problematic with small operations, but if you have large operations, it can really count. And we demonstrate this also in our latest research tool that goes from RISC-V standard RISC-V instructions to ternary assembly, and then we compare basic RISC-V to this ternary assembly, which is based on RISC-V, and show that these bit flips are much less in the ternary variant. So bit flips are important. If you have, if we would have hardware that is suitable for ternary, then also you would need less transistors, right? So then you also need less static power, right? Because each power leaks a little bit, even if they're off, and if you have millions of them, then that little bit adds up. So So that's static power and dynamic power. Inversion operations. If you invert a balanced ternary signal, since it's balanced around 0, a 0 inverted becomes a 0. So there's no bit flip there.
Yeah, I think this is especially useful when we're talking about the transition from positive numbers to negative numbers. In two's complement in binary, we need to flip everything and add a 1, right? And in balanced ternary, we only have to flip the 1s to -1s and also the other way around, and we get the negative representation. It's really elegant in that way.
Yep. The carries are also less. Like if you go from 1 to 2, you have to flip, right? And if you go from 3 to 4, you need to flip again everything, right? So going from 1 1, which is a 3, to 1 0 0, right? Which is a 4. Then you have 3 flips.
Yes, and each of those flips will consume some amount of energy, right?
Dynamic power.
Yes.
Yep. Arithmetic. So with balanced ternary, it's really easy to go for both addition and subtraction, right? Because you just if you have a logic gate with 2 inputs and 1 output, then the first input could be a positive number and the second output could be a negative number.
Yes.
Right? So then you could have 1 plus -1 is 0. So it's the arithmetic is really elegant as well. The rounding to nearest integers is truncation. So if you have balanced ternary, the average, the expected value is 0, right? So if each symbol is equally likely, then a 1 or a -1 or 0, they're equally likely. So the average is a 0. So if you remove that, then that 0 is the rounding is the same as truncation. Semantics when modeling is also really interesting. For example, there's many sort of ternary signals, control signals that we can model, like a DC motor going forward, backwards, or no rotation, light being polarized X, Y polarized or no light, magnets being interacting, repelling, or no interactions. Obviously, traffic light, logic being true, false, or unknown. So there's many types of things that we can model very compactly, like efficiently with ternary.
So what about this Radix economy argument, which I presented in my video, as you said, maybe not fully accurately. If you could go into more detail into that and fix the errors that I made.
Yeah, sure. So, first of all, it's not a trivial topic, and there's quite a bit of discussion around it. So this is not a fault on your part. It's just not really clear. But having said that, let's try to make it a bit more clear. So we have computers are symbol processors, right? They work with an alphabet. And when I talk about ternary, I always say the computer alphabet goes from 2 letters in your alphabet to 3 letters in your alphabet. So humans have, for example, English, 26 letters in our alphabet. And I would say that language is quite powerful. But computers, they have only 2 or 3 letters in their alphabet. And if we want to encode information those are the two letters that we have to do to use, right? That's the only things that we have. And the way we construct unique symbols is to stack them together and then give a meaning to it. So in the case of a number, we're using this positional numbering system. So we learn in school the base 10, the Radix 10 positional numbering system. So this is what you see on your screen, the number 1125, right? In actuality, we can interpret this slightly differently by saying this is 5 times 10 to the power of 0. 10 to the power of 0 is 1, so 5 times 1 is 5. Plus 2 times 10 to the power of 1. So 10 to the power of 1 is 10, 2 times 1 is 20. So 20 plus 5, 25, etc. Right? So the way we encode numbers is using this positional numbering system. So we have positions, in this case 4 positions, and each position has a radix. So a number from 0 to 9, in total 10 different unique symbols. All right? Now we have a function which we call the radix economy, which says what is the optimal radix by looking at the complexity of each position. So how many numbers, unique numbers, do we define in one position? So if we have radix 3, we have 3 different symbols. If we have binary, then we have only 2 different. Radix 10, we have 10. On the one hand. And on the other hand, we have the amount of positions. And now we are getting this sort of tug of war, right? So on the one hand, we want to minimize the amount of positions. And on the other hand, we want to minimize the amount of unique positions that we need to have per device, per position. And this can be interpreted in a different way. So a position needs to have some implementation in hardware, right? So if we have a memory cell, let's say a capacitor, then this capacitor can hold 2 types of charges. It's either charged or not. But actually, a capacitor is an analog device, so it can also help a middle charge, right? So, for example, you charge it fully, or you charge it to a half state, which is interesting, because now we have the same device, right? We have exactly the same device, but we're using it for different radices. We give it more or less unique symbols. And obviously we need to differentiate between those signal values in that single position. And that adds to complexity. You understand?
Yes, I fully understand.
So now the idea is we have a device that is more or less complex, and on the other hand we have area, like silicon area. How many of these devices can you fit into an area? And to encode a number, let's say we have the number 1125. We need 4 positions to represent that number, right? In decimal, multiplied by the radix, so the unique amount of signals that each position can hold. So we have a cost function of 40, right? So we can see that here. So we have, for example, the number 100 I use here, 3 different positions. Each position can have a number between 0 and 9. So the cost function is 30. Base 3, we need to encode the same number 100. We encode it as plus plus minus 0 plus. We have a cost function of 15. If we have a binary, we have the number on 100, we have a cost function of 14. Now, you see that for some numbers, especially in the beginning, binary is actually more economically efficient than any other radix. And that is only for a finite number of numbers, and especially in the low range. So if we have an architecture that is, let's say, lower than 16 bits, then there are several numbers which can be more efficiently encoded than in binary than in any other radix. So far, I hope it's clear, but there's a couple of twists to this interpretation, to this function, and that is the model, the cost function itself, right? So what we do in this function is we give equal weight to the amount of positions and the complexity of the device, right? It says R times W. It doesn't say half times R times, 1/4 of R times 3/4 of W, right? So it's equal importance. So we are saying that the area is equally important as the device complexity.
Which is probably not true in the real world, given the costs of certain things. This might not scale completely with the complexity of hardware, right?
So indeed, so if we think about scaling, then in the end, what we want to have as much as possible, as many devices as possible, such that we can, so that we have redundancy and we can do all kinds of things. That is one aspect. But the reason why it's so complex is that when we look at other aspects of computing, especially the effects of going smaller and smaller and smaller, we see that communication is becoming a much bigger problem than computation. So if we want to communicate information from memory to the ALU, the arithmetic logic unit, and do an operation like an AND or an OR operation, right? It takes the equivalent of 1,300 ALU operations in terms of power if we want to communicate something. So it's 1,300 times more costly to communicate information than to process the information. And this is only getting worse. Why? Because when we go smaller and smaller and smaller, the communication doesn't scale as nicely as the logic. So the memory doesn't scale as nicely as logic. So what will happen is that you get this gap that widens. And what people do is they try to put as much memory around the cores as possible. And this is a I would say almost a nasty image, right? So you see how memory is getting stacked everywhere to be as close to the ALU as possible, so that there is no communication overhead.
And I could imagine that here ternary computing or representing data in ternary could help with that due to more density of information on one line.
Exactly. So then, if we go back to the Radix economy, now you can see why this cost function is so complex, right? Because now we can say maybe the complexity of the device actually is more important than the area, because if we cannot use the area because it consumes too much power, and we need to do all kinds of mitigation to sort of reduce the amount of heat that comes of it, then maybe it's better to use a more complex Radix, and then less area for that. But the overall result of the system is that we have a faster, more power efficient system.
Yeah, so I can see how we could approach this Radix economy from multiple perspectives, and I think there still wouldn't be a clear answer here, right?
Indeed. And now in my thesis, I tried to sort of separate two things. I tried to separate logic, so using the Radix economy for logic, and the Radix economy for memory. So for memory, I feel it's more straightforward. So we can like with a capacitor, we can model this multiple states with a single device, right? So you get this model of 2 to the power of n and 3 to the power of n for ternary, and it's very logical that to see that this ternary here has the maximum advantage, because it's a single device, and the comparison is fair if we try to make it fair. But for logic, it's much more complex, right? Because with CMOS, we departed from this idea that every state in binary is a single device. So you would say that with binary, and you see this in all these videos, that with binary, you have a switch that's on and off. So when it's off, it's a 0, it's on, it's a 1. That's not what happens with CMOS.
Yeah, this was also what happened, what I showed like in my video to simplify binary, that it's also a switch. But yeah, in CMOS, we have the PMOS and the NMOS, right? So it's actually 2 devices to represent 1 bit.
Why? Do you know?
You could tell me, Professor, please.
So the reason is that you need to have a very clear 1 and a very clear 0. And if you switch transistor, you always need to pass this voltage threshold, which is about 0.7 in silicon. Meaning that if you want to have a really good 1, then, and you have only 1 transistor, then it is the VDD, let's say 1 volt. It's a little bit less, let's say 5 volt. 5 volt minus this threshold voltage, 0.6. So you never get this perfect 5 volt signal, right? It's always 5 volt minus 0.6 volt if you switch it. And the other way around as well with a logical 0, you never get a perfect 0, because you need to overcome this voltage threshold. So to get this reel-to-wheel logic so that you can propagate the signal with the maximum noise margin, we're using pull up and pull down networks, right? Pull it up and pull it down to a good logical 1 and a good logical 0. That's the reason. So we're getting to a point where we actually encoding numbers, binary numbers, with 2 devices.
Yeah, and speaking of that logic and encoding, I'd like to read you one comment that was posted on the video. I think it's one of the most popular comments on there. So the user Akulkis wrote, "I'm a computer engineer. In college, I looked into using negative voltage, no voltage, and positive voltage to represent -1, 0, 1, or even 0, 1, 2 numbering systems. And frankly, the circuitry needed to represent even a simple adder or subtractor more than doubles the number of transistors and diodes needed for each logic gate. 50% more information per bit, but 100% more circuitry is a net loss." What is your perspective on this?
Yeah, so it is true that you might need more devices to create ternary circuits, but as Henning Gundersen, my colleague, said and demonstrated in his thesis, you can also make ternary adders that need less components than with binary. By exploiting the analog dimension, right? And I would say that one of the big reasons why ternary has not become a real big thing is that especially for logic, if we talk about memory and if we talk about communication, then ternary is a big thing, right? So a lot of people don't know that, for example, GDDR6X and GDDR7 use physical ternary signals. USB 4.2 uses physical ternary signals, Thunderbolt 5, etc. Memory since the 2000s, solid state drives are multiple levels, right? So you now have quad bit or even pentabit levels. So 32-bit levels per 5-bit, so it's 32 states per memory cell. So we have multiple levels, including all the circuitry that is needed to handle that. For memory and for communication, but we don't have it for logic, right? So that's why I often show this sort of overview where we can go to non-binary memory, non-binary communication, but as soon as we want to do something with it, then we have to switch to binary logic. So a lot of the issues have to do with binary hardware. So we need new devices that can efficiently encode and switch ternary signals. And one way to do it is with carbon nanotube field effect transistors. Why? Because these devices, they can be changed with different voltage thresholds by just changing the diameter of the device. Sure, you could also change the voltage threshold in regular CMOS. So that's also really interesting because then you just utilize existing technology. But with carbon nanotube field effect transistors, you are getting to the foundational limits, and that is, in my opinion, important. So for demonstrating the true benefits of ternary.
And what about this research from South Korea, this tunneling-based ternary metal oxide semiconductor? Is this something big in the field? Could this change something in this regard to this ternary logic computation thing?
Yeah, well, it's certainly really cool to see that researchers are doing things at wafer scale, right? So not a single prototype. But to be honest, I've seen work in the 80s as well, where people have done things at wafer scale. So it's not that ternary is sort of rediscovered now in the last 5 years or something. So it's always been there in the back of many people's minds, but the technology was not really ready. And I think what's interesting with the TCMOS paper is that they demonstrate that it's still possible, it's still there. There are some challenges, of course, related to speed. So the middle state, if you create that middle state through voltage division, then you burn quite a bit of power, right, to get to that middle state. And the result is that you typically reduce your switching speed. So then, if it cannot be used for, let's say, CPUs in your laptop, then the market will be a bit less, right? It will be a niche. And this is great to start with, but if we really want to have this this paradigm to be embraced, it needs to be as fast as binary. It needs to be as efficient as binary. It needs to be as cost effective as binary. So it needs to have these what we call VLSI metrics, very large scale integration metrics, like performance, power, area, and costs. If ternary is equal to these three, then as four cost is shown, then it can be a worthy competitor, and worthy competitor only when ternary is not 2% better, right? It needs to be significantly better. Otherwise, you're not going to change the whole technology stack.
But do you think this is possible, given the current state of research, the current momentum, the direction? Is it possible that it could become much more efficient than binary if the industry pace would be there, if there would be real work put into developing hardware on a large scale? Do you believe that ternary is the way to go beyond the Moore's curse limitations?
Yes. So I would be it would be weird for me as a ternary researcher to say no. So there's a bias here, of course. But I truly believe it as well. I truly believe it, and the reason is that I see more and more industry picking up multi-valued logic. So multi-valued logic is anything beyond binary, right? So ternary, quaternary, and we see this in all kinds of research. Sometimes they don't call it ternary, or sometimes they don't call it multi-valued logic. They call it multi-level or multi-bit, or have all kinds of names. So in my thesis, I have a whole word cloud of synonyms. So the industry is adopting this and standardizing it. So we're seeing that this paradigm is being looked at. We also see, this is one of the last slides that I had. We see that, for example, in this industry roadmap from Devices and Systems, IRDS, that there's a huge focus on efficiency, right? So with all these AI chips that need a lot of data movement, they need a lot of bandwidth, they need a lot of data processing. At the moment, that data movement is a real problem. Like I said, it costs a lot of energy and also a lot of time to move data. So what if we have a more efficient architecture, more efficient devices, more efficient software stack also built on top of that? Then we could push beyond what we have now. And I think what is interesting here is that this was maybe one of the questions in your audience as well about noise margins.
Yes. I have the comment here. I could read it to you if you want.
Yeah.
Bank 1449 wrote, "Hello, computer engineer here. The problem is the signal to noise ratio. Sure, ternary is fine, but the problem is that sampling these values is hard, especially at high speeds. You would have to make voltages further apart to count for this, meaning more power used, meaning slower speeds, or just slow down speeds to account for this."
Yeah. Yes. So he's right that the noise margin is halved by for ternary, and Shannon in his famous paper on communication theory, he also demonstrated this. But he also demonstrated that you could encode the same information with ternary as well. And the only thing that you need to handle is the signal to noise ratio. And this is the thing. What if your signal to noise ratio is good enough so that you can increase your radix, right? So what if you have overhead that allows you to increase the radix? And then it's mathematically sound and also physically sound to go to a higher radix. Regardless that we sacrifice a bit of noise margin. The problem with binary is that it is the most simple way to encode information. It's also the fastest way to process information. But what if fast is too fast? What if your material cannot handle those speeds? You're reaching material limits. And this is what happens, right? So this paper by Micron, they are responsible for making these memory chips that you find in NVIDIA GPUs, for example. They discovered that actually by going from binary to quaternary and then going to ternary makes a lot of sense. Why? Because the device complexity was reaching its limits by going faster and faster and faster. Because what these GPUs want, they want to double the amount of bandwidth every generation, right? So to double the amount of bandwidth, you either double the frequency or the information density, or you double the amount of pins, right? The amount of pins is a physical limit. So you just have a fixed amount of pins that you can have on a chip. It's just a physical area. So you cannot just infinitely double the amount of pins. So what is left is you can double the frequency. But if you are at super high frequencies, then your signal gets attenuated, gets gets dampened, such that you don't have a lot of room for such that you get all kinds of artifacts, right? So you get errors, bit loss, and so forth. So what if instead of doubling your frequency, you double the amount of information? You encode your information with more physical levels. So we're trading frequency for Radix. And that is in this Shannon-Hartley theorem. So I would, if people are interested in that, just look in this book by Pierce. It's an old book. He was one of the mentors of Shannon, actually. It's this is a second or third edition or something. And that one will show really elegantly how it's easy to exchange bandwidth, which is W, with signal to noise, which is P over N, to increase the channel information, the information density. So if we use it with a 2, log 2, it's measured in bits per second. If it's measured in threes, then it's in trits per second. But that doesn't change the density. It's just the interpretation of the signal. What does change the information density is this R, this P over N.
Dr. Steven Bos, everybody. Thank you so much, Doctor. I know we're a bit over the time threshold, but as you can see, I think we only tackled the very top of the iceberg. I think we could talk for hours and not run out of topics. So maybe if this goes well, we could schedule a call once your semester clears up a bit, your calendar clears up a bit, somewhere in the future.
Love that. I would love that. It's a really exciting field of research that I'm in. It's I see more and more videos popping up also on this topic, on ternary computing, on aspects of more efficient computing, and they're all very much related. So one sort of closing remark that I'd like to give you is that if you compare it to other paradigms, ternary computing is basically a form of classical computing, right? It's an extension of the traditional computing we know and love. So a lot of the logic is the same for ternary, except it's a little bit more complicated. For other paradigms, you have like optical or quantum or probabilistic or you name it, biological. They are more radical differences, and none of the paradigms have this sort of possibility of completely replacing binary. None of them have that. Why? Because, for example, quantum computers, they're really good with a tiny bit of information processing, but they need traditional hardware to do the pre-processing, the post-processing. They need a traditional hardware to do all the side things, except maybe a tiny bit, which is the computation part itself. And the same holds for probabilistic and for other types of paradigms. There's always trade-offs, and the reason why binary is so popular is that the industry has poured massive amounts of cash into it to get this very fine balance between the metrics that we're interested in, the VLSI metrics. So we used to have all kinds of different logic families for binary in the 60s, in the 70s, and the 80s, and in the end, CMOS emerged as the winner of all these different logic families. And I think this is the most important part, that binary is not going away, but rather all these these other paradigms, they are sort of extending it or complementing it. And that's how I see ternary as well. I don't see ternary as a replacement for binary. I see ternary as a really good accelerator for some kind of problems.
Join the largest ternary and multivalued logic conference by IEEE, the International Symposium for Multivalued Logic. This year, the 56th edition of ISMVL is in Japan. The link to the call for papers is on the screen right now and also in the description of the video.